the number of factors, right? Now onto the factors, the meaty part of it, right? Which is what all of you would be knowing. If a number can be written in the form a power p into b power q into c power r, goes on where p, q, and r are prime. That's important. They also have to be prime. Then the number of factors of this number equals p plus 1, right? Not going to get into the proof and the explanation of that. P power plus 1 into q plus 1 into r plus 1, right? All the powers plus 1. But you need to remember this. A lot of people miss out on this. The sorry, not PQR, where A, B, and C are prime, right? Where you have written it down in the prime factorized form. The bases over here are going to be prime. Where A, B, and C are prime, that's the condition. Only when that happens, you write the number in the prime factorized form. Prime factorized form. Only then can you apply this formula to say number of factors is p plus 1 into q plus 1 into r plus 1, right? So that's important. So once again, any natural number represented in the form a power p into b power q to c power r, where a, b, c are prime numbers, right? They have this many factors that are natural numbers. Because one can say that, you have negative numbers divisible as well. So therefore, if you're looking at only positive integers or natural numbers, this is the case. And the question will typically qualify. But if we're not saying natural numbers, just saying integers, right? That means you just need to multiply it with 2, because for every positive integer, we also have a negative integer. So the number of factors is going to be this into 2, right? The negative integer should also be considered. But typically in the CAT, and so far we've seen only positive integers being asked. Anytime you should be ready with the other way around as well, right? So let's take up a simple example and see as to how to do it, right? So how many factors are there for 10 power 4 into 6 cube into 45 square? We need to find the factors over here. Quickly, power plus 1 5 into power plus 1 4 into power plus 1 3. No, can't do this. Can't do this. Conditions are important. Are these prime? They are not. So we need to prime factorize them. It's been written in some form, right, with some exponents, not in the prime factorized form. How do we do that? 10 power 4 is nothing but 2 into 5 whole power 4. Next is 2 into 3 whole cube. And the next is 3 square into 5 whole power 2, right? In the exam, you should be, I mean, if you're quick, you can directly deduce from this. You know, it's a 2 power 4 into 2 cube. That's a 2 power 7. Or you can look over here and do it. What about 3 over here? 3 power 4, 3 square whole square, right? So 3 power 4 and a 3 cube gives me a 3 power 7 as well. What about the 5s? 5 square, 5 power 4. That's a 5 power 6 over here. 5 power 6 over here. So how many factors are there for this number? Number of factors. And by factors over here, I'm speaking about positive integers, right? Should have been a little more clear probably. But number of factors when typically asked referring to positive integers is going to be power plus 1 into power plus 1 into power plus 1. 8 into 8 is 64 into 7, 420 plus 28, 448 becomes the answer for this question, right? So number of factors. So remember again and again, prime factorized they have to be. Otherwise, you're just incorrect, right, with your approach. What about number of odd factors for a number and even factors, right? We'll take up this example, but before that, number of odd factors of a number. So if we have a number written as 2 square into 3 cube into 5 power 1. Odd factors over here is what? I don't want 2's over there. Ignore the 2's, refer to the rest. What do we get? Power plus 1, 4 into power plus 1, 2. That comes to 8. What are the total factors? Total factors is going to be, we need to consider 2 squares. So power plus 1, 3 into 4 into 2, which comes to 24. Or even factors over here is nothing but total minus odd, right? Total factors, all numbers, all factors are going to be odd or even. If 8 are odd, the remaining 16 are going to be even over here. And that's it, right? 16, subtract over here, total minus odd. So likewise, for this particular example, how do we find out? Do not directly get into the powers. Need to check for the bases. Are they primes? No. So 2 power 4 into 2 cube is 2 power 7. I'm left with a 3 cube into a 5 square, right? Into a 5 square. And what are we getting over here? Now, how many odd, so can go for the total factors. Total factors over here, power plus 1, 8 into 4 into power plus 1, which is 3. That's going to give me an 8 into 12, 96. Even factors over here. Yeah, sorry, odd factors to begin with, right? Ignore 2 power 7, 3 cube into 5 square, that's going to be 4 into 3, 12. Even factors over here is going to be 96 minus 12, which is 84. Now, is there any way in which we can directly get even factors from this? Yeah, the formula or rather observation is this. For the rest of them, take power plus 1, 4 into 3. But for 2 alone, 2 power 0 is not allowed. So you have to go with 7 itself. Not 7 plus 1, but 7 itself. 7 into 4 into 3 will also come to 84. In case this is fine, you can logically understand it, use it. If not, at this stage, you can just go for total factors. Minus odd factors is even. And how do I find the odd factors? Ignore the 2's, find the number of factors. And that's it. That's the answer for this question. Huh? 12 over here, 12 odd factors and 84 even factors. Okay. Move to the next one. The next concept over here is that pertaining to factors that are perfect squares or cubes, right? So factors that are perfect squares or cubes, if we're going to be given a question like, let's say 2 power 7 into 3 power 6, how many perfect squares, right? How many how many squares of positive integers, perfectly divide n? If I'm going to perfectly divide this, I'm a factor, right? For a number to perfectly divide this, it's a factor. So how many factors, right, are going to be squares of positive integers? So for me to get squares of positive integers, so I have to rewrite them as something square, right? Prime square, or rather, I need each prime over here as a square, sorry, right? So 2 square whole power what is 2 power 7. 2 square whole cube, and there's an extra 2, okay? 3 power 6 is nothing but 3 square whole power 3, right? That's it. The extra 2 you can ignore over here. Now, what you have is over here 2 square whole cube, 3 square whole cube, right? The number can be, in that way. All factors of this, right? So now 2 square and 3 square are prime squares. Once you have done that, then apply the same formula, power plus 1 into power plus 1. The answer over here is 16. 16 numbers over here are perfect squares. If they're asking for perfect cubes or something like that, 2 power 11 into 3 power 17, let's say, right? 17 or 16, let's say. Then this number can be written as 2 cubed whole power. As it's perfect cubes, I want to find out, right? Not writing the question down. If you have to find out the perfect cubes, I mean factors are perfect cubes, 2 cube whole power, what is less than 11? 2 cube whole power 3, right? 2 power 9 we get. Into 3 cube whole power 5, I can go up to 5, right? Okay. Now I apply the power plus 1 and power plus 1 because these are prime cubes in the required way, right? So 4 into 6 over there, 24 factors are there for this number, which are perfect cubes, okay? And what is the smallest such value? It's going to be 1 cube itself, right? 1 cube is 1, and that's a factor itself. Now, around this, a cat question turned up, right? 2019, slot 2. How many factors of 2 power 4 into 3 power 5 into 10 power 4 are perfect squares which are greater than 1? Trap was laid over here, right? Now I want perfect squares, okay? So the concept is prime square whole square, right? Prime square whole power whatever. And one more trap was laid over here. That is 10 over here is not prime, right? So we need to prime factorize. So 10 power 4 can be written as 2 into 5 whole power 4. Now we have to rewrite this number as the n as 2 power 4 into 2 power 4, which is 2 power 8. 3 power 5 remains 3 power 5. 5 power 4 is 5 power 4. Now if you want to write this as perfect squares, what are the perfect squares going to be? 2 square whole power 4, 3 square whole supports up to square, 5 square whole square, right? The extra 3 we can write separately or ignore it also, doesn't matter. Once we have written in the prime square format, the number of factors over here is going to be what? Power plus 1, 5 into the power plus 1 into the power plus 1. And that's 5 into 9, 45. And was a type in the answer. And then there is last bit of wordings over here in this question. They're saying which are greater than 1. They don't want 1. They want it to be greater than 1. If I'm listing out all the factors, my factors will start from 1. But they don't want 1. Is 1 a perfect square? Yes. 1 is a perfect square. So therefore, it would have been counted in this 45. So that 1, which is a perfect square, which has been counted in this 45, has to be subtracted. And 44, therefore, becomes the answer for this question. Now, is this tough? Conceptually, yes. In terms of solution solving, hardly anything. In terms of conditions to be applied, yes. So quant over here, short questions could still be loaded with conditions. Every few words could mean another extra condition which is being added. Okay. Moving to the next concept over here, where we need to express expressing as a product of two positive integers, right? I will just take it up with some examples over here. In how many different ways can 24 be written as a product of two positive integers? Okay, 24 over here can be written as, try to manually go about it, 1 into 24, 2 into 12, 3 into 8, 4 into 6 over here, right? Done. So we can just write 4 ways, right? 4 ways it can be written. But if you want to build a formula around it, 24 is nothing but 2 cubed into 3. Number of factors equals power plus 1 into the power plus 1, which comes to 8. The number of ways in which you can write as a product of two positive integers, right? Two positive integers is nothing but number of factors divided by 2, which is 8 by 2, which is 4. 24 is written as 1 into 24, smallest into largest, second smallest, second largest factor, and so on. If you have 8 factors, you can write it in 4 ways. That's it. Right? That's for the product of two positive integers. If the question just says product of two integers, not positive, it can also be negative. How? You can also write it as minus 1 into minus 24, minus 2 into minus 12. Two minuses become a positive, right? So therefore, for every one way with as two positive integers, we have another way for negative. So it becomes 4 into 2, which becomes 8, right? Long story short, 24 number of factors over here is 8. Number of ways you can write as product of two positive integers, 8 by 2. Number of factors by 2, which is 4. Product of two integers and not positive only. Instead of direct writing it as number of factors formula, write it as for positive whatever value you got into 2, right? So which is 8. So 4 and 8 are the answers for these two. Okay, we'll take up one more over here around the same, but what if I end up making the wordings a little more complex? How many ordered pairs A comma B exist such that both A and B are integers, okay, and modulus of A into modulus of B equals 24? That's it. It's the same concept, but the wording is taking it in a different direction, right? But we need to understand product of two numbers is 24. Should both be positive? No. Should both be negative? No. One can be positive, other can be negative as well, right? A and B, because a modulus is being applied over here. That's it. So 24 over here can be written as 1 into 24, 2 into 12, right? 3 into 8, 4 into 6, and all of that. Now, simple thing, ask yourself as to how many values A can take. A, if it's only positive, A can take the values of, you might feel 1, 2, 3, 4. No, it can be 24 into 1, 12 into 3 as well, 12 into 2 as well, right? A can take 8 positive integer values, right? What are they? 1 into 24, 2 into 12, 3 into 8, 4 into 6, right? It's ordered pairs. We need to be careful. The previous question just said, how many ways can you write this? Product of two integers, right? The order is not mentioned. Here it's ordered, right? The order matters. Can be 6 into 4, 8 into 3, 12 into 2, 24 into 1. A can take these values and B can take these values. Now, A can take 8 positive integer values, for which B can also take another set. Now, modulus is there. So, for each of these positive integers given over here, right? Let's say 1 and 24. You have mod 1 into mod 24. You can also have mod minus 1 into 24 plus 24. You can also have mod minus 1 into negative 24. You can also have um, uh, 1 into minus 24, right? 4 ways, right? 2 where this is negative, and 2 where it's positive, right? The other can come. So in the sense, A can come for every such pair identified. A can be written in 2 ways, B can be written in 2 ways, positive, negative, and positive, negative. That gives me another 4 ways, right? So 8 positive integer values. Once you identified, each of those can come in 4 ways, plus minus and plus minus. The answer over here becomes 32. This becomes a difficult question conceptually, right? But in terms of solving, once you understand how it is, the way it works, it's going to be pretty quick, right? Pretty quick. So 24 over here, number of factors itself, 8, because any of those A can take, and they're all positive factors, right? 8. Um, Once you've found that for each of these 8, B is going to be the other value. Now both can be positive or negative. So into 2 into 2. So 8 into 2 into 2 comes to 32. That becomes the answer, right? Conceptually, if you understand it, then it becomes easy. Okay. Moving to the next concept quickly. Is one of the longer lessons over here. Need to push through. Right, product of factors. We'll just take it up with the example directly over here. So, what is the product of all the positive integers that are that perfectly divide 36? That simply means product of factors. The word factors has not been used. Positive integers that are dividing 36 perfectly and all is given. Right. The formula is simple. The product is nothing but the number into x by number into x by 2. That's it, right? So 36 over here can be written as 1 into 36, 2 into 18, and so on, all right? But if we need to multiply each of these, right, what are we getting? We're getting a 36, a 36, a 36, a 36, and a 6 is nothing but a 36 power 0.5. So if you multiply all of them, you're going to get a 36 power 4.5. But you don't need to do all of that. 36 is nothing but 2 square into 3 square. Number of factors over here is nothing but 2 plus 1 into 2 plus 1, which is 9. So the product of all the factors is nothing but the number 36 to the power of 9 by 2. That's it. It can be a decimal. Don't worry about that. 4.5. It will be taken care of because um, it's uh, you can write it as 36 power half whole power 9 as well, right? And what is root of 36? 6. 6 power 9. If it's there in the options, that becomes the answer over here. Okay. Moving to the next concept, that pertaining to the basics of remainders, right? So that's important. Um, Again, it's something to do with dq plus r, which we just saw. A number can be written as dq in the format of dq plus r. The only important thing you need to remember at this stage is that if if um, uh, if you're going to be dividing a number by 23, let us say, how many different remainders can I have? It can be from 0 to 22. The number of different remainders is going to be 23 remainders. Whatever is the divisor, that many remainders I can have. It's going to be 0 to 22. But if all numbers in a number system has to be written in the 23k format. Now, what is this 23k? Divisor 23, 23 into some quotient. I don't care, right? Then what are the possible formats? 23k plus the first remainder 0, 23k plus 1, 23k plus 2, and so on till 23k plus 22, right? It's used quite often, this format, especially in questions pertaining to progressions. It'll be quite handy, right? So therefore, just remember and see if you can write down numbers in this manner when it comes to solving some of the questions. Okay. Now, HCF concepts with remainders, right? HCF concepts with remainders. The first major concept over here, in fact, we just take it with a couple of examples, right? Um, Something not pertaining to it, remainders per se, but yeah, this is a ZAT question. A chocolate dealer has to send chocolates of 3 brands to a shopkeeper. All the brands are packed in boxes of same size. The number of boxes to be sent is 96 of brand A, 240 of brand B, and 336 of brand C. These boxes are to be packed in cartons of same size containing equal number of boxes. Okay. So you have a huge carton, right? Visualize. Within that, you're putting small boxes, right? You're putting inside. There are 96 boxes of brand A, 240 of brand B, and so on. Okay. Each carton should contain box of the same brand of chocolates, and they're all same size. Equal number of boxes are to be can be fit inside. And in one carton, each carton, boxes of same brand has to be used. So if this is a brand A, only brand A can be used. Fine. What could be the minimum number of cartons that the dealer could use? If I want to use very few cartons, I have to put a lot of boxes. If I want to put a lot of boxes, right? If there are 96 and I have to equally distribute them with nothing remaining, right? Nothing remaining over here, what do I do? What do I do? So to put a lot of boxes, I have to find the largest number divisible by each of these 96, 240, and 336. I have numbers like these. You can use common division, right? Nothing wrong with that. 96, 240, and 336 divisible by 12, all of them. 8 over here, and then 20, and 12. 2 12s are 24, and then an 8 again. And I know that 4 is definitely divisible by all of them, right? So that's going to give us 4 you divide, and you're going to get 2, 5, and 7. Now, what is asked over here? What could be the minimum number of cartons that the dealer has to send, right? HCF over here, 48 boxes per carton. If you're using 48 boxes in each carton, if that can it can be supported, you're putting that's the maximum number of boxes we can put into a carton. Then how many cartons were used for brand A? From this 96, you divide 48. That is, you divide by 12 and by 4, and you get a 2, right? That's going to give you the number of cartons, right? All the way in the bottom, there's nothing but the number of cartons. For brand B, 240 boxes. If it's 48 boxes per carton, 240 by 48 is nothing but what we got over here, 240 by 12 by 4, right? 5 and 7. 2 plus 5 plus 7, that's the minimum number of cartons, right? 2 plus 5 plus 7, which comes to 14. Option 2 over here becomes the answer. Okay, moving to the next one. So another example, now actually this one more pertaining to remainders, right? When each of 100, 125, 150, and 200 is divided by a natural number n, the remainders are 4, 5, 6, and 8 respectively. What is the largest possible value of n? This is more like the lesson, example, right? N over here are 100, the numbers 100, 125, 150, and 200, right? N over here can be written as dq plus r. Now, they're all being divided by the same natural number n, same divisor d, right, or n. And they're getting 4 different remainders. What are the remainders over here? 4, 5, 6, and 8. From these numbers, if I remove the remainder, if I remove the get rid of the remainder, I'm going to be left with the dq format, right? 100 minus 4 is 96. 125 subtract your 120, 144, and 192, right? That means once I get rid of the remainder, that number is divisible by the divisor. From 100, if I get rid of 4, 96 is divisible by the divisor. 125, I get rid of the 5, it's divisible by the divisor, 120. Right, so 96, 120, 144, 192 are all divisible by that divisor, natural number n. What is the largest possible value n can take? What is the largest possible value which is divisible by, which is going to perfectly divide each of these? What can d take the largest value? HCF. That's the HCF concept with remainders, right? The first one. If the remainder over here is going to be removed from each of them, right? 4 different remainders, and then you apply the HCF, you're going to find the largest possible value of n, which is going to do that. So 96, 120, again, to find the HCF over here, take the differences, that will also do. Difference over here is 24, difference over here is 24, difference over here is 48, right? You can also find out the HCF of differences. For 24, 24, and 48 over here, 24 is the answer, right? So 24 is the, and you know that 24 is also perfectly is going. I mean, 96 is perfectly divisible by 24. So 24 over here is the answer. Or you can just divide all of them and also do it. But you can also look at the differences and note it. Yet 96 is going up by 24. If 96 is divisible by 24 and it goes up by 24, that is also going to be divisible by 24. And the same happens over here, right? So that's the concept. And moving to the next example of the same concept, let's see with remainders. One where we don't know the remainder, but it's all the same. So, what is the largest positive integer that divides 88, 39, 102, and 60 and leaves the same remainder, right? So, let me reorganize and write it down as 39, 60, 88, and 102, right? Now, we're going to use the concept we did earlier, right? So, if a number is going to be in the dq plus r format, dq1 plus r, if I want to add some value to it, and I still have to get it in the dq2 plus r, the same format. Remainder is the same, leaves the same remainder. What is the number I can add to it? The number I can add so that the remainder remains the same. The remainder has to be the same in both cases. I have to add a multiple of the divisor. I can add any dq3 or whatever, right? I can add a multiple of the divisor and I get a fresh divisor into quotient, right? The remainder remains intact. So 239, what was added to get 60? 21. To 60, what do we add to get 88? 28. To this, we added 14, right? The largest positive integer is nothing but the HCF of these. That's it. What's the HCF of these? That's 7. 7 becomes the answer for this question, right? So it's a lesson example. In case you're not clear, just refer to the lesson, right? It's a standard thing. Hopefully, it serves as a revision for all of you, right? Now on to the part which is fun, right? Which is LCM concepts with remainder. That I think a lot of you generally like it. So two specific concepts over here when it comes to LCM. You need to know that a number when divided by a number when divided by A, B, and C, right? A, B, C individually leave the same remainder. Yeah, same remainder R, let's say, right? What is the number format? That number format is nothing but K into LCM of A, B, and C, and then you have an R, right? When you divide by A, remainders are, divide by B, remainders are, C also, then this is the format over here. So in the sense, in if a number divided when divided by 2, 3, and 4 leaves the remainder 1, right? What's the number format over here? LCM of 2, 3, and 4, that comes to 12. 12k plus 1. The smallest number which satisfies is going to be 1 itself. What's the next one? 12 into 1 plus 1, 13. Next, 12 into 2 plus 1, 25, and so on. Take, for instance, 25 by 2 gives me 1. 25 by 3 also gives me a remainder 1. 25 by 4 also gives me a remainder 1. It will definitely satisfy. When can we apply this? When the remainder is 1 everywhere, right? It's the same remainder. But we can have a negative remainder, right? What if we divide a number by 3, 4, and 5, right? When we take a number and divide it by 3, 4, or 5, the remainder comes to, let's say, 2, 3, and 4. Which means this remainder over here, it can also be written in the form of a negative remainder. What is that? Subtract the divisor. 2 minus 3 is what? Minus 1. 3 minus 4 is minus 1. 4 minus 5 is minus 1. Now these are same. Now given that these are same, once again, k into LCM of 3, 4, and 5. And then the minus 1, the remainder. That's it. The negative remainder, right? So n can be written this way. N can be written as 3, 4, 5. LCM is 60, k minus 1. The smallest number, smallest positive integer is going to be when you put a k value of 1, and we're going to get 59. Next is going to be add another 60, 119, add another 60, 179, and so on, right? Take 59, for instance, 59 by 3, 57 is off, remainder is 2. 59 by 4, 56 is off and remainder is 3. 59 by 5, 5 is off and remainder is 4. It will definitely satisfy. Negative remainder is another pattern you have to look for. Now, where it's not, where neither of these exist, then Chinese remainder, we'll be seeing that separately. But as a question turned up, yes, question is turned up pertaining to this, and it was a word problem. What do we have? A school has less than 5,000 students, okay? And if the students are divided equally into teams of either 9, 10, 12, or 25, exactly 4 are left out. And I'm dividing into groups of 9, 4 are left over. Remainder, if I'm dividing into groups of 10, 4 are left out. That's the remainder. All right. So what is the format? The number of students in the school, which is less than 5,000, is nothing but k into LCM of 9, 10, 12, and 25. Now, how do I find the LCM of this pretty quickly? All right. I would prefer doing this, right? So 9 and 10, what is common between them? Nothing. HCF is nothing. If HCF is 1, then the product 90 is the LCM. You can do 2 at a time, right? 2 at a time is perfectly fine. Now, 90 and 12, what's common between them? 6 is the HCF, right? 2 is left over. So you can make that a 180. What is common between them? 5 is common. Another 5 is over here. That's it, and you get a 900, and 900 becomes the LCM of 90, 180. I mean, sorry, 9, 10, 12, and 25. 9, 10, 12, and 25. You can do that way, or you can go in for the plain old simple way. The common division is just going to be a little time consuming. Time consuming because you have to go with primes. Start with 3, and you're getting 3, 10, 4, and 25. 3s are done, 2 is there, 3, 5, 2, and 25, and then a 5 is there. You get a 3, 1, 2, and 5. 2 5s are 10, 10 3s are 30, 3 2s are 6 5s are 30, 30 into 30 will also give you 900, right? Whichever way you want to do. Or you can also look for highest power of the primes, right? We know that 2, 3, and 5 are the primes. What are the highest powers of the primes used here? 5 square, 25. 3 is what? I think 2. 2. 2 square is here. 2 power nothing. 2 power 1 only over here. 2 square. That's it. 2 square into 3 square into 5 square. 2 into 5 whole square is 100. 3 square is 9. Whichever way, you're going to get 900 pretty quickly, right? So back to this, LCM of 9, 10, 12, or 25 is going to be 900, 900K plus 4. That's the number format, right? Total number of students is of the form 900K plus 4. Only then when you divide by 9, this gets cancelled, 4 are left out. Or by 10, this gets cancelled, 4 are left out, and so on. We've seen that in the lesson, right? So, however, if they are divided into teams of 11 each, then no one is left out, right? That means this number is perfectly divisible by 11. Can also be written as 11A, 11A. That's it. It's perfectly divisible by 11. So the maximum number of teams of 12 each that can be formed out of the students in the school. Now we need 12 each. Okay. So how do we find that? We need to find the number of students in the school. N is less than 5,000. What's the smallest value it can take, right? It can take K can take a value of 0. If K is 0, then what are we getting? 9 into 0 plus 4, 4. 4 is possible. 11 multiple, no, right? Next, if K is 1, what are we getting? 904. K is 2, 1804. Then 2704, 3604, 4504, and we stop with that. Which of these is going to be divisible by 11? For 11, what do we know? Alternate digits, right? Plus and minus and plus. 13 minus 0 doesn't work out. Plus, plus, minus for the rest. Works out. 12 minus 1, 11. 1804 is divisible by 11, right? So that is going to be the number of students. What is asked is number of teams that can be formed. 1804, right? Divide by 12. What are we going to get? 15 I mean, 112s are 12, and then a 65, right? 60 over here, and then we get a 0, right? In fact, yeah, 604, you can put in 600 and a 4 here. So 150 over here becomes the answer. Um, Again, seems long when you're doing it for the first time. I'm just trying to break it down and do it. But if you're very clear with the concept, then applicability, I'm not saying it's very easy. LCM of 4 numbers, if you're quick with that, you need a 25 multiple, you need a 4 multiple. So it's definitely a 100 multiple. Yeah. And 3 power is going to be 2. So 900. Those of you are quick with this, 900A plus 4 has to be a 11 multiple. So 904, 1804. When you notice 12 minus 1, this works out. That's it. You can take 1804 and divide by 12. You can just use the calculator if you wish directly as well, right? So what do we get if we use if we get a 1804 divide by 12? The quotient is 150. The remainder is 0.3333, right? Which is 0.333 into 12, which is 4. So the quotient is what matters. That many teams can be formed. 150 becomes the answer over here, right? So now that's the LCM concept with remainders. On to this thing called Chinese remainder. When do we use? Whenever this link doesn't happen, right? This link doesn't happen. That is when divided by a number. I mean, there's no common remainder or like common negative remainder, something like this. What is the sum of the smallest and third smallest positive integers that leave remainders of 1 and 6 when divided by 3 and 14 respectively, right? We should quickly be able to write the number as what? When divided by 3, the remainder is 1, 3a plus 1 number format. D into some quotient plus remainder, dq plus r. Next one divided by 14, b plus remainder is 6, right? Now Chinese remainder, what do we see in the lesson? Keep the smallest coefficient variable on one side, 3a equals 14b plus 5, a equals 14b plus 5 by 3. This is similar to, we are concerned only about the remainder. 14 by 3, what's the remainder? 2. 5 by 3, remainder is 2. What is the smallest value of b, which will make sure that 2b plus 2 is divisible by 3? 0, 1, or 2 works, right? Then we are getting 6, right? 6 is divisible by 3. So b equals 2 can't be plugged in over here. B equals 2 has to be plugged in over here to get the number. So the number is what? 14 into 2 plus 6, 28 plus 6, which is 34. But what plus 34? LCM of the two devices. LCM of the two devices, 3 and 14, which is 42. 42C plus 34. That's the number format. What is the smallest number? Smallest when C equals 0, we're getting 34. Third smallest, right? Or rather, yeah, so smallest and third smallest. This is the first smallest, then we have a second smallest, then we have a third smallest. So C is 2. Smallest is first smallest, right? Is what? 0. Second is C equals 1. Third is C equals 2. Plug in C equals 2. We get an 84 plus a 34, which comes to 118 over here. You add the two of them, you're going to get 152, right? So 152 becomes the answer for this question. Okay. So that's Chinese remainder, right? Chinese remainder over here. And does it come too often? Not too often, but yeah. Application is there in some questions, so knowing it will definitely be helpful, right? Now, successive division with remainders, we've seen this. The lesson example is what I'm using here. What are the smallest and fourth smallest natural numbers that leave remainders of 1, 3, and 2 when successively divided by 3, 4, and 6 respectively? Okay, so we know what to do. The divisors we write first, 3, 4, and 6. Here it's successive division, one after the other. The previous questions weren't. So the remainders in the next row, 1, 3, and 2 over here, respectively, is well given. So we're going to start with, we're going to ignore the last divisor over here, right? From bottom, when we're going up, we multiply, then we come down, right? So how do we go about this? Bottom to top 2 into 4, 8 plus 3, 11. 11 into 3, 33 plus 1 comes to 34. Right? So 34 over here is the smallest number which satisfies. As I go up, I multiply. As I come down, I add, multiply, and add. 2 into 4, 8. 8 plus 3 is 11. 11 3s are 33 plus 1, 34. 34 is the smallest number. So 34 is the smallest number. But what number format? What into K? It's going to be this time around, not the LCM, but the product of divisors, 3, 4, and 6. 3 into 4 into 6. That's 24 into 3, 72. 72K plus 34 is the number format. The smallest over here, right? Smallest is for when K is 0, we're getting 34. The fourth smallest, right? This is the first smallest. Fourth smallest is going to be when K equals 3 more. 3 more is going to be 3. And 3 into 72. 72 into 3 is 216 plus 34. That's coming to 250. Right? So those are the values. 34 here and 250. Okay. Moving to the next concept, that pertaining to some product and exponents. Don't have an example or question here, but it's a concept we need to remember, right? So what if we need to find the, let's say, the remainder of some number like 5634 plus 3456 plus 7823 divided by 5. What's the remainder? We don't need to add all of these up and then divide and then check as to what's the last digit, right? We can individually find the remainders and do it. To find the remainder when divided by 5, we are concerned only about the last digit, right? Only about the last digit. 4 by 5 remainder is 4. 6 by 5 over here, remainder is 1. 3 by 5 remainder is 3. The sum of all of this, 4 plus 1 plus 3 by 5. And that is going to come to 8 by 5, which is 3. What if it's going to be product in place of plus if I'm going to have the multiplication symbol? It's the same treatment. It's going to be 4 into product of the individual remainders. 4 into 1 into 3, that's 12. 12 by 5, which comes to 2. 2 becomes the answer in the case of product. Now, when it comes to exponents, there are two things which I need you to know. What is going to be the remainder when 36 to the power of 45 is divided by 5? Now, the base over here can be divided by the remainder directly. The power can't be touched right now. Euler's torsion, we'll come to that soon. But the base over here can always be directly divided by 5. And the remainder can be written down. 36 divided by 5, remainder is 1. Right? 36 can always be divided by 5 and remainder can be noted. What is the remainder of 1 power 45 by 5? That's 1 itself. That's it. Right? What's the logic for exponents over here? The base can be divided by the divisor and remainder can be noted. We are only concerned about the remainder. Now, what if we need to find the remainder of 34 to the power of 46 by 5? Right? What happens over here? Negative remainder we could work with. Right? What's the negative remainder? 34 by 5 remainder 4, we know. Right? But what is the remainder? When we keep subtracting the divisor, we get the remainder. What if I subtract 5 once again? Right, from 4, we are left with minus 1. Minus 1 power 46 by 5, and that is nothing but 1. That's it. We can straight away get this. Right? Now, what if it's going to be the other way around? 34 power 47 by 5. If it's going to be odd, then what are we going to get? We're going to get remainder of minus 1 to the power of 47 by 5, and that's going to be minus 1 by 5. But I don't want a negative number. I can always add back the divisor and bring it to the positive form. That's 4 becomes the answer here. So if when you divide by the divisor, the base, if you're going to get 1 or minus 1, you can quickly close it out irrespective of what the power is going to be, right? So that will be the best way of closing those questions. Now, what is Euler's torsion over here? Euler's torsion, there is a, clear formula over there. Now, Euler's torsion is just going to find out the number of positive integers, right, less than n that are co-prime with it. Co-prime means no other common factor other than 1. HCF is 1, right? So pi is a symbol over here which is used. Pi of n is nothing but n into that number into 1 minus 1 by x1 into 1 minus 1 by x2 and so on, where x1, x2, x3 are, and so on are distinct primes. Distinct primes over here, prime factors of n, right? So we have something like 24. We have to find 4. It's going to be 24 into 24 can be written as what? 2 cube into 3. Distinct primes are 2 and 3. Forget the power. That doesn't matter. 1 minus half into 1 minus 1 by 3. That's 24 into half into 2 by 3. Simplify and you get 8. 8 is the Euler's quotient of 24. Right? Could you be asked for Euler's quotient? No. Could you be given a question which speaks about find the number of integers less than positive integers less than a number which are co-prime with it? Might be there, right? It could be there. So it could be, you should be prepared for it. Okay. But where does it get used? It gets used in Fermat's little theorem, right? Fermat's little theorem. And we'll take it with an example, right? We've seen this in the lesson for sure. If you're given a question like 37 to the power of, let's say, 17 divided by 24, right? What's the remainder over here going to be? Now, I know that 37 can be divided by the divisor and the remainder can be noted. The power over here can be divided by the Euler's quotient of the divisor, provided 37 and 24 are co-prime. Right? That's the condition. 37, 24 are co-prime. Therefore, I can go ahead with this division, noting the remainders. So what is it? 37, I can divide by 24. 17, I can divide by Euler's quotient of 24. We just did that, and that's 8. And what do we get? 37 by 24 is 13. 17 by 8, remainder. Remainder is what is being done everywhere. The remainder is 1. And that's it. 13 becomes the answer over here, right? So what's the logic? If 37 and 24 are co-prime, base by the divisor, power by the Euler's quotient of divisor, and write down the remainders, and that's Fermat's little theorem over here. All right. Okay. So moving to the next concept over here, right? Or what if the base and the divisor are not co-prime? We could use Fermat's little theorem only when they are co-prime. Or they are not co-prime. Let's take up an example. 18 to the power of, let's say, a 283 divided by 45, right? It's not co-prime 1845 because 9 is there, right? So in which case, when you have 45 over here, you have to break it as 3 square, 9 into 5. First step is to prime factorize them. What is the remainder when this is divided by 9 square, right? Break it into two cases. Remainder of 18 to the power of 283 divided by 3 square over here is going to be 0. It's perfectly divisible by 9. That's it. As it's perfectly divisible by 9, the number can be written in the form 9a. Now, what about 5, right? Remainder of 18 to the power of 283 divided by 5. It's going to be 18 by 5, power by Euler's quotient of 5, which comes to 4. Here I can apply it because 18 and 5 are co-prime over here, right? Co-prime. 4 is going to be the Euler's quotient of 5 because for a prime number, Euler's quotient is 1 less than it. That's it. Just apply it. 5 into 1 minus 1 by 5. 5 is the only prime number, right? So you're going to get 5 into 4 by 5. So Euler's quotient of a prime number is going to be 1 less than it, right? And what do we get? Remainder of 3 to the power of 3 over here by 5 and 27 by 5. We're getting a remainder of 2, right? 2 over here. So therefore, this number format can be written as 5b plus 2, right? 5b plus 2. Let me just quickly make sure there's no mistake over here. 18 by 5, 3, fine. The power over here is 283, right? Yeah, that's fine. And yeah, so we get a 3 power 3 over here. 3 power 3 is 27 by 5, which comes to a 2. So it's going to be 5b plus 2. So 9a over here should be equal to 5b plus 2. That's the number format. And when is that going to be? And that's going to be when start plugging in values. You can directly start plugging in values for b over here, check if it's a 9 multiple, right? Or rather than go the Chinese remainder way, which we saw. So 0 is 2, no, 1 is going to be 7. Look for the next one, 12, keep adding, 17, 22, 27, it works out. When b is 5 years, it works out. We're getting 27. So 27 over here becomes the answer, right? So when base and divisor are not going to be co-prime, you have to prime factorize. And the reason why it was not co-prime, that would have given a remainder of 0. 9 is definitely there here, right? It's cancels perfectly. 5, you write it separately and continue. And then you bring it back in the Chinese remainder way. In the exam, if something like this comes up, I would say no, don't really go for it. It's going to be a little too much, right? Avoid, look for easier questions which can be quickly answered, right? Now on to 4 types before we pick up some questions, right? 4 types over here, special types, 4 or 5 special types which I have in the lesson, right? Where you have the difference of squares of positive integers, right? Where you have a number, in how many different ways can you write it as the difference of squares of positive integers, right? So you need to understand, you have to break it down into 2 categories. Those in the those which are odd numbers, those which are 4 multiples, right? And those which are 4k plus 2, right? 4k plus 2, which is even numbers which are not multiples of 4. How many ways can this 4k plus 2 be written as difference of squares of positive integers? That is a square minus b square format. These numbers can be written in 0 ways. Now for these two, what do? We have to take up, you have to find the number of factors of k. That is, divide this 4k. If the number is 4k format, divide by 4, find k, right? And you have to divide this by 2, right? If n is the number is going to be divisible by 4, you first divide it by 4, then the number of ways it can be written as a difference of squares of positive integers is simply going to be number of factors x, right? Whatever it's going to be, x by 2, right? So this particular one is going to be the number of factors of this number, right? Of this number k, where k is odd itself, by 2. In this case, I have to divide it by 4. In this case, I don't need to divide by 4, write it as it is. Technical stuff, just refer to the lesson once again. Can't go into depth in a revision over here. So any which wish, we'll quickly look at an example over here and the application. If you know it really well, it can be done quickly. How many different ways can 48 be written as the difference of squares of 2 positive integers? A square minus b square is 48. Multiple of 4, divide by 4, you get a 12. Now 12 over here is 2 square into 3. Number of factors divided by 2. Number of factors is power plus 1, 3 into the power plus 1, 2 divided by 2. That's going to be 3 ways. Answer becomes 3. Know the concept really well. Question turns up, it's going to be pretty quick. But one such question has come in the past. I'm not able to locate the specific year. Something like this, which came up, right, quite some time back. Where a and b are positive integers, how many ordered pairs a comma b exist such that a square minus b square is 194, right? And what is 194? It's in the 4k plus 2. It's not divisible by 4. As it's not divisible by 4, the answer is 0. You can quickly mark it and keep going. That's it. If you know the concept, there's no workings at all. There's nothing. Just need to mark the answer and keep going. It did come up in one of the CAT years, one of the early years, right, before 2010. Okay. Then sum of 2 or more consecutive natural numbers. In how many ways can n be written as the sum of 2 or more consecutive natural numbers? This is a very standard type, can come up quite often. It's nothing but number of odd factors minus 1, right? You just need to find the number of odd factors over here and then subtract 1 from it, and that's it. That's the only concept. Proof and all of that is not very important right now. Just see as to how to solve it, right? How many ways can you write? 120 is a sum of two or more consecutive natural numbers. 120, first you prime factorize it. Divisible by 8, 2 cube. We're left with 15, 3 into 5. Number of odd factors is what? Forget this. 2 into 2, right? Power plus 1 into power plus 1, which comes to 4. Subtract 1 from it. That's it. 3. In 3 ways you can write it. What are the exact ways that you'll have to list out, right? That hasn't really turned up. But yeah, so 3 ways that, if you know, I think to that extent it's enough, right? Sufficient from an exam perspective. Okay. So now on to very quickly, we're coming to the last part of this lesson. Remainder theorem for algebraic expressions. Where a is a constant, the remainder when a polynomial f of x is divided by x minus a is f of a, right? So what does this mean over here? What does this mean over here? So if let's just take it up with an example over here, right? With an example. So just a second. Yeah. Okay. So we have to take it up with an example over here. This is how it's gonna be, right? So what is the remainder when this polynomial, right? This f of x over here. And what's a polynomial? A polynomial is one where the powers are all non-negative integers, right, of the variables 4, 3, 2, and 0 in this case, right? 8 into x power 0, minus 8 into x power 0. When this is divided by something in the x minus a form, but I have x plus 3. What do? I can write it as x minus of what? Minus 3. I reconvert it, right? So now my a is going to be minus 3. The remainder is simply f of a. That's it, right? Also see this in the quadratic equations lesson. So just f of minus 3 you plug in over here. You're going to get minus 3 whole power 4 minus 3 into minus 3 whole cube plus 2 into minus 3 whole square minus 8. Minus 3 whole power 4 is 81. Minus 3 into minus 27 is a plus 81 again. 9 twos are 18 minus 8, 162. This is a plus 10 and it comes to 172, right? So standard thing, remainder theorem. We'll also see it in the quadratic lesson. We're revising that part in detail. Don't want to spend too much time on this. Okay. On to something called the Wilson's theorem, right? Don't memorize the formulae. Just understand the application. That'll be enough. If your denominator is going to be a prime number and your remainder is, your numerator is a factorial which is 2 away from it, 35 factorial by 37, remainder is 1. The remainder of 36 factorial by 37. What's the difference between these two? I'm multiplying with the 36. So multiply 1 with the 36 and you get a 36. That's it. If you have to remember the formula way, it's going to be n minus 2 whole factorial by n, where n is prime and the answer is 1 and all of that. Just remember it with an example. You need to note that 37 over here has to be prime, right? Then n minus 2 factorial, right, is going to be 1. And n minus 1 factorial in the numerator is going to give me that itself, that n minus 1 or 36, whatever it is, right? So therefore, a remainder of 45 factorial by 47 is going to be 1. Remainder of 46 factorial by 47 is going to be 46 into 1, 46. But if you're going to be asked something like, what is the remainder of 46 factorial by 48? Answer is 0, because this over here is not prime. 48 can be written as 2 into 24. Both 2 and 24 are there. Perfectly cancels out. You get 0. So this applies only if your denominator is going to be prime. How often does it turn up? Really not much, but if it does, you should know how to answer it. Now, remainder when terms are in GB is the last part of this lesson. What is the remainder when 2 plus 2 square plus 2 cube and goes on till 2 power 50 is divided by 7? Right? These type of questions, we have to see if 7 can be written as sum of some 2 powers. 2 power 0 is 1, 2 power 1 is 2, 2 square is 4, 2 cube is 8, exceeding 7, stop. Now, 7 can be written as sum of 2 or more of these. Yeah, 1, 2, and 4, you add up at 7, right? 4, 5, 6, 7. So, every 3 consecutive terms, right? When added up is going to be a multiple of 7. Why do we do that? If you're going to have something like 2 power 37 plus 2 power 38 plus 2 power 39, right? Then 2 power 37, if you take out common, we're getting 2 power 0 plus 2 power 1 plus 2 square. That's equal to 7. 7 multiple. Every 3 consecutive terms a multiple of 7. It's perfectly divisible. I can ignore those. Sum rule. I'm concerned only about the remaining terms. So 1 to 50, there are a total of 50 terms. How many 3 consecutive terms can we remove? Right? 50 divided by 3. What is the remainder? 2. We're left with 2 terms. 3 at a time. I can remove these, the next 3 and so on. I'm left with 2 terms in the end. What do I prefer? Do I prefer the first 2 terms? I can remove any 3 consecutive, right? Do I prefer the first 2 terms or the last 2 terms over here? I would definitely prefer the first 2 terms. They're easy to work with. Remove 3 at a time from the end. All of these are removed, right? All of these are removed. And we are left with the first 2. So what is the remainder of 2 power 1 plus 2 square divided by 7? 2 plus 4, 6 divided by 7. The answer becomes 6. Right? So that's it. So that's it when it comes to factors in